Hi everyone. Today we are going to discuss about polynomial ADTs or else polynomial abstract data types. So we already discussed about abstract data types. So here today we are going to discuss about polynomial abstract data types. Arrays are not only the data structure in their own right, we can also use them to implement other abstract data types. So we always know that arrays are the only linear data structure, but other than that, there are other data types like list, stack, queue. They are all linear data structures. So we can use the kind abstract data type of array and implement other data structures like ordered or linear or list. And so there are some examples for list, like days of a week, values in a deck of cards, floors of a building, years the United States fought in World War II, and etc. These are some of the list of items. Okay. So we can perform operations like in array we are performing different types of operations. Likewise, we can also perform many operations in list, including find the length, while in array we will be we will be as declaring a length of array. Like that we can also declare length like find the length of an list. Also read the list from left to right, retrieve the ith element, store a new value into the ith position, insert a new element at the position, delete, and etc. These are some of the operations that we can do in a list. Rather than the state that formal specification of the ADT ordered list, we want to explore briefly its implementation. Perhaps the most common way to represent an ordered list is by an array where we associate the list element 0. So we can also represent an ordered list of an array by using by the list element 0 with the array index I. So using the array index I, we can also represent it as a list by using the element 0. We will refer to this as sequential mapping because using the conventional array representation, we are storing ai plus 1 into consecutive locations I and I plus 1 of the array. This gives the ability to retrieve or modify the values of random elements in the list in a constant amount of time. So what they are saying is like we can actually likewise we are storing a consecutive numbers like if 3 4 5 etc. We can also save the data like adt ordered list in a sequential manner. um, um, we can access the list elements values in the either direction by changing the subscript values in a controlled way. So we can do all these the list of operation we have already mentioned like addition, deletion, etc. We can also do it using the polynomial ADT. Okay. Let's discuss a problem for requiring ordered list, which we will solve by using one-dimensional array. So we will now check on a problem where we needed the ordered list, and by using the one-directional array, we will solve it. This problem has been the classic example for motivating the US of S processing techniques, which we will see in the later chapters. Therefore, it makes sense to look at the problem and see why arrays offer only a practically adequate solution. The problems call for building an identity for the representation and manipulation of symbolic polynomials. So so using the ordered list, we can using the one-dimensional array, we can solve the ordered list, like problem requiring ordered list. So we are going to check how it is done and how it is represented using an ADT and manipulation of symbolic polynomials. By symbolic polynomials, we mean the list of coefficients. Coefficients in the sense that the number before the variables. Like for example, 3x is a polynomial and x will be the variable and 3 will be the coefficient, and exponents that accompany a polynomial. Example, two such polynomials are like x square is an exponent, and 3 cube is an exponent. So these are the exponents and coefficients in a polynomial. And example for such polynomials are a of x is equal to 3x square plus 2x plus 4. We are going for some example. So uh, we have mentioned two polynomials like 3x square plus 2x plus 4, and 4x plus 10x cube plus 3x square plus 1. So the largest or leading exponent of a polynomial is called its degree. So we have to know about some polynomial things like the degree. A degree of a polynomial is the largest exponent they have. Like in the first example, it is square, so the degree is 2, and the second example, it has a cubic factor, so the degree will be 3. So for different polynomials, the degree depends upon the exponents they have, and coefficients that are 0 are not displayed. So there is a value for a polynomial where the coefficients are 0. So terms which exponents equal to 0 does not show the variable. So if the exponent is 0, it doesn't show. And if there is any missing values, like if there is a cubic factor, square factor, and there won't be any x factor, and only the constant part. So the x part is not visible in the sense that the value of x is 0 at that part. So that is how we are implementing polynomials. And the term with exponent equal to 0 does not show the variable, since x raised to power of 0 is 1. There are standard mathematical definitions for the sum and product of polynomials. Assume that we have two polynomials. A of x is equal to sigma ai xi. Similarly, we can define subtraction and division on polynomials as well as many other operations. We begin with an ADT definition of a polynomial. Particular operations in part are a reflection of what will be needed in our subsequent program to manipulate polynomial. So we'll go for an example, or like go for the program to see how it does. So let us now consider how we can represent a polynomial in CPP using by defining a private data members of polynomial as follows. So first of all, we create a degree, int degree, and coefficient to tell us the polynomial of which degree, and the coefficients to assign. And maximum degree is the constant degree representing the largest degree polynomial that is to be represented. And here it should be less than or equal to maximum degree. The degree should be less than or equal to maximum degree, which is the largest degree you can represent. And coefficient should be maximum degree plus 1. So the coefficient should be at least the maximum degree plus 1. Now, if A is a polynomial class object and n less than or equal to maximum degree, then the polynomial A of x would be represented as note that the A coefficient of I is the coefficient of x and minus I, and the coefficients are stored in order of decreasing exponents. This leads to very simple algorithm for many of the operations on polynomials: addition, subtraction, evaluation, multiplication, etc. And the second type is like representation is using a degree is much less than the maximum degree. Like in the above one, we have said that the maximum degree should be less than or equal to the degree, but here it should be much less than the maximum degree. Then most of the position in a coefficient of 0 and the coefficient of maximum degree are unused. To avoid this waste, we define coefficient so that its size is a degree plus 1. This can be done by declaring the following private numbers by using private integer in the degree float coefficient and adding the following constructor to the polynomial, like adding the following constructor to polynomial, like polynomial scope resolution operator because it is used outside the class, and the polynomial of int d D will be the degree, and coefficient will should be in a float, as we already assigned it, and it should be degree plus 1. So it will be assigned as coefficient. And the representation tree includes solves the problem mentioned earlier. It does not yield a desirable representation. So to see this, let us consider polynomial that to e many terms. So such polynomial are called sparse. Like if all of the most of the coefficients are 0, then we can say it as a sparse matrix, like sparse, and we can say it as a pass. For instance, the polynomial 100 plus 1 has two zeros, the terms, and 990 has one 100 like 4 by 4 matrix, or 100 by 100 matrix. Then the most of the numbers are zeros, and only one will be only one of the element will be one. Then we can say it as a sparse matrix. Suppose we take the polynomial a of x defined above and keep only its non-zero coefficients. They will really have the polynomial. All our polynomial will be represented in a single array called ter term term array. Each element in term array is of type term, which we will be defined below. Since a single array term array is to be shared by all polynomial objects, we declare it as a static class data member of polynomial. So if you want to represent in a single array or term array, we can use you can use it like a we can use it, and we have to define the term in each element as term type term, and which will define below, and the single array term array is to be shared by all polynomial objects. So let us see how it is declared. So let's look at an example. Class polynomial. We have declared a class polynomial, and inside the class polynomial, we have declared a polynomial friend function, friend, and privately we have declared coefficient and exponent. And the private members of a polynomial are defined as follows: like private, a static term array of a maximum term, static in free, in start, comma finish. So word maximum term is a constant. So maximum is a constant, and the required term definition of the static class members outside the class definitions are term polynomial. We are declaring it outside the class, so we are using scope resolution operator and term array of maximum terms. Int polynomial free is equal to 0 or 1 depending upon the memory location. So consider the two polynomials a of x is equal to into 1000 plus 1, and p of x is equal to x 4x into 10 raised to x square x cube plus 3x square plus 1. These could be stored in an array as shown in figure 2.1. Now let's start off. Note that a dot start b dot start give the location of the first term a and b respectively, whereas a dot finish and b dot finish give the location of the last term of a and b. The static class members freeze give the location of the next free location in the array, 10 array. For example, a dot start is equal to 0, a dot finish is equal to 1, pt start is equal to 2, b dot finish is equal to 5, and free is equal to 6. The array here, like 2 into 1000, and coefficient exponents are varied here. So it is represented in different columns and blocks, and we are representing start a dot finish is equal to 2. So it's in second position, and b dot start is equal to the third position, and b dot finish is the first position. Free space are in the last position. So this is an array representation of two polynomials. This is how we will represent the polynomial using array. In general, any polynomial a that has n non-zero terms has a dot start and a dot finish, such that a dot finish is equal to a dot start plus n minus 1 if a has non-zero terms. That is, a is the zero polynomial. So it is clear that if a dot finish, if there are two terms, a dot finish and a dot start, we have to a dot finish is equal to a dot start plus n minus 1. So it will be lesser than that. And if it is only possible if there is a non-zero terms in the array, in the polynomial. Now let's discuss about polynomial addition. Let us now write C++ function to add two polynomials, a and b, to obtain the sum c is equal to a plus b. So we have two polynomials a and b, and we have to obtain the third polynomial c, which is the additive of a plus b. It is assumed that representation 3 above is used to store a and b function adds and a of x and b of x term by term to produce c of x. The basic loop of this algorithm consists of merging the terms of the two polynomials depending upon the result of comparing the exponents. The switch statement determines how the exponents are related and performs the proper action. Since the test within the switch statement require two terms, if on one polynomial runs out of term, we must exit the loop. The remaining terms of the other polynomial can be copied directly into the result. Terms of C are entered into the term array, starting the position free by calling function new term. In this case, there is not enough space in term array to accommodate the C, an error is printed and the program terminates. This is the polynomial function for CPP program for adding two polynomials. In first, we have declared the polynomial function, and after that, we have declared some variables to in like start, b dot start, c dot start, free, and etc. And after that, we have checked the condition if a less than equal to finish and b less than equal to b dot resolution is finish is true. If it is true, then we compare the term array and the exponential term array and exponential. If the in such case, if it is lesser or greater than or equal to, we have given three cases. If it is lesser or equal to or greater, and depending upon the cases, it will go to the it will increment the array, and after that we have given a addition operator for adding the polynomials in regarding the exponents, and after that we finish it by c dot finish is equal to free minus 1, and we'll return the third polynomial, which is the additive of a and b. So analyzing the addition, it is natural to carry out analysis in terms of the number of non-zero terms in A and B. Let M and N be the number of non-zero terms in A and B respectively. The assignment of line 4 are made only once and hence contribute 0 of big of 1 for the overall computation time. So for computation time, the polynomial addition requires big of 1, and if only if it is a non-zero terms of n numbers. And if either n is equal to 0 or m is equal to 0, the while loop of line 5 is not executed. In case either m or m not n equals 0, the while loop of line 5 is entered. Each iteration of the while loop requires big of 1 time. So each iteration in the while loop will require the big of 1, which is okay, which is a medium amount of time to receive to iterate, and at each iteration the value of a or b or both increases by 1, since the iteration terminates when either a or b exceeds. So if either a or b exceeds, the value of a or b exceeds, it will take it will increase by 1 to finish the iteration. A dot finish or b dot finish respectively, the number of iterations is bounded by m plus n minus 1. So for a dot finish and b dot finish, the iterations number will be respectively of m plus n minus 1. The worst case scenario will be worst case is achieved for instance consequently. So if it is if the number of iteration is bounded increase, then it will create an m plus n minus 1 iteration. That will be a worst case scenario for the polynomial addition. So I hope the lecture helps you for the polynomial abstract data type. See you in the next class. Thank you.